Okay, welcome to this morning's session. Our first speaker is Richard Bergmeier. Richard Bergmeier is a native Austrian. He comes from Linz, but has been studying in compatriots. He's been studying at the University of Cambridge in UK. It's Cambridge, UK, not Cambridge, Massachusetts. And the talk he's going to give today is basically a report on his master's thesis there. For those who've been into computers for some time, well, you may remember that natural language querying of databases was a big thing back in the late 70s, early 80s, and was then completely swamped by the advent of graphical user interfaces. This was a point when basically interest in those natural language querying issues more or less subsided. Probably also because, well, natural language interfaces are always a difficult thing to do and it didn't really work out very well back then. But now we're much smarter. And so Richard's topic for today, for the first talk, is a natural language database interface using fuzzy semantics. So, first, one thing, if you've got questions, please use a microphone. There are people watching this via web stream. There'll be people watching this afterwards on video, and they won't understand you if you don't use a microphone. So, Richard.
Thanks for the introduction. Thanks for the introduction. As the chair already said, natural language database interfaces have already been around, but now there are two things that make the situation today very different from what it was in the 70s. One is that database technology has gotten a lot better, and the other is that linguistic front-end processing and linguistic grammars have gotten a lot more broad coverage and a lot more robust. So, as the chair already said, this came out of some work I've done on my MPhil thesis in Cambridge, so I'd first like to thank my supervisor and Copestake. Then I'd like to thank Ulrich Bodenhofer at the Johannes Kepler University in Linz for helping out with the fuzzy logic related bits of this. So he's really been very helpful throughout my work here. And then I'd like to thank Ted Briscoe at Cambridge and Daniel Oscherson at Princeton for reading some of the related manuscripts, and thanks to a whole bunch of people for participating in the experiment. What is the overall idea of a natural language database interface? Well, you simply have a natural language expression that you use to state your information need. For example, I'm interested in a hot, dry city, or I'm interested in a large city near San Francisco. And then this can be resolved against a database that actually has data about cities and cities being near others. So what you see up here is a screenshot of a prototype we've actually done. And you can give it an expression like hot, dry city, and it will give you a ranking of records in the database, ranked according to the degree to which those records fulfill our intuition about a hot, dry city. So that means that for the top-ranked cities, we see that they all have very high average year-round temperatures. They all have very low number of wet days in a year, so that is really what we understand as a hot, dry city. And then as you look at the lower ranked records, you see that temperatures tend to decrease, number of wet days tend to increase. So this is really the intuition. This sort of ranking is what we want to have if we're interested in a hot, dry city. So how does all of this work? Well, the basic assumption we make here is that there is natural correspondence between the way we define a data model and the words we use in natural language to refer to certain objects in the data model. For example, we can have a table. That table is place, and we use a noun like city to refer to a record in that table. So for every record, we will have attributes like name, so we can use an identifier like San Francisco, and that turns into a lexical item. So when we say San Francisco, we actually address a specific record within that table. And then you can have a population attribute, so that population will turn into an adjective that's like a big city, a small city, a dry city, a rainy city. So there will always be measurements that you can use to determine those. And then you have, for example, of course, those entities enter into relations. So those relations are, again, represented by tables. For example, you can have the distance between two places. So an attribute of that will be the number of kilometers between those two cities. And then you use words like near and far from. So I'm interested in a city near San Francisco, stuff like that. So from a linguistic point of view, what we're really interested in is we have an expression like a small city near San Francisco. And then, of course, if small turns into a logical predicate, like small of x, where we know that x is a city, and the question is, what does small of x really mean in terms of the population of x? What does near prime of x and y mean in terms of the distance between x and y? So in linguistics, that problem is known as vagueness, and it's involved in determining the meaning of stuff like small and near. Now, before I go into all of the detail of how this works, let me just tell you where I'm coming from with this. The reason why I'm speaking to the hacker community today is because I'd really like to see some technology transfer happen here, and I'd like to see this technology transferred into open source projects and stuff like that. So what you see up here is a screenshot from what is actually a scientific prototype. And there's nothing wrong with that prototype, but its purpose is simply to demonstrate some of the points I had to make in my thesis and to bring to a proof of concept the sort of software I was envisioning. But the software I actually have is far from a sophisticated software package that you can just use out of the box to do something nearly useful. So if you're sitting here today and you say, well, this is kind of too cool technology, I'd really like to start an open source project or something like that to make this kind of stuff happen and to make a useful piece of software out of that, then I'd really like to encourage you to come and see me afterward. So I think there can be no greater success for me for this talk here than inspiring some of you guys to go out and do useful and cool stuff with this. But what I will talk about right now is, first of all, putting fuzzy semantics to use in a closed domain question answering system. So I'll give you all of the broad ideas about how to construct this natural language database interface. Then I'll talk about vagueness and fuzzy semantics, sort of the linguistic background that we need in order to determine whether or not what we're doing here makes any sense. And then I'll take a step back and talk about fuzzy logic as a generalization of bivalent logic, which is gave rise to this nice subtitle that what I want to do is, wild speculation about the nature of truth and other equally unscientific endeavors. So the first thing we will get rid of in terms of science is the assumption of the excluded middle in logic. So in a classical bivalent logic, we say that A, such as, for example, the set of all small cities, is a set on the domain of all cities if and only if there is a characteristic function mapping a certain city to zero if x is not a small city, and mapping x to 1 if x is a small city. So there can only be two truth values, 0 and 1, and there's nothing in between. But that's not naturally what we're doing, right? Naturally, what we have is continuous measurement here, such as the population of a city. And then all we can do with this sort of model is we have to define a threshold. So we can say that assumption in terms of the logic, which is that there are infinitely many truth values in the unit interval. Not only 0 and 1 can be a truth value, but every value in between 0 and 1 can also be a truth value. And that means that we can make a more realistic assumption here, and we can say that every city with population up to, I don't know, 10,000 is perfectly matches our prototype of a small city, and then every city with population over 1 million or so is definitely not a small city anymore. And in between, we do some kind of linear interpolation. So if we have a city with population 70,000, then maybe that's a small city to degree 0.7 or something like that, where that degree doesn't really matter all that much in itself. But the point is that we can use those degrees to actually rank those records. So we can come up with a ranking of cities ranked according to the degree to which they are small cities. And this actually naturally maps into stuff that you can actually observe in the way people use language. So what we've done here is we've asked 20 people about buildings. So if a building is built in 1960, is that an old building, yes or no? So we asked that 20 people, and we see that for the question, I don't know, 1940, there's very high agreement about the fact that, yes, this is an old building. And then as you approach 1975 or so, there is minimal agreement about whether or not a building built in 1975 is still an old building or already a new one or whatever. And then the function rises again. You get higher agreement again for 1995 or so, when there is reasonable agreement again that a building built in 1995 would have to be would not be called an old building anymore. So this is the agreement we observe in the way language is used, and this naturally translates into a characteristic function like this. And the idea of this characteristic function is that you give it the year in which a building was built, an attribute that you can actually have in the database, and it will return the degree of oldness of that city, the degree to which something matches our idea of being an old building. So that means you can take a natural language expression like hot, dry city and directly translate it into a select statement that looks like this. So this thing is what linguists call an n-bar phrase or noun phrase in a way without the determiner. So the idea is that you have a noun in there, city, and that noun actually tells you that you're looking at a place table. So I'll tell you how we define that mapping later, but the point is there is this mapping. So you select an entity x, and that's from the place table, and then x will have a temperature attribute, a rainfall attribute,